does is only as good as the engine that turns it. Because without a propeller, the airplane wouldn't fly. Well, the same thing could be said for the work a compressor does and the drive unit that runs it. Without being coupled to a drive unit, the centrifugal compressor wouldn't move 1 cubic inch of gas. This is the third section of a 3-section module covering centrifugal compressor principles. In this section, we'll look at various drivers and methods of coupling them to the compressors. We'll also see how flow is controlled to produce the correct gas pressure. Centrifugal compressors are available over a fairly wide range of speeds, anywhere from 3,000 RPM on up to as high as 50,000 RPM. Therefore, the type of power unit used depends on the desired speed range, loading of the compressor, and available fuel sources. In higher speed and load applications, the steam or gas turbine is the most commonly used. Now, in low speed or small load compressors, electric motors are sometimes used. Let's take a closer look at these different drivers. In steam or combustion gas turbines, speed increasing gears are often needed between the turbines and the compressor shaft and are connected with couplings. Commonly, steam and gas turbines use speed increasing gears between the turbine and the compressor. Steam and gas turbines generally rotate at high speeds and therefore can sometimes be used to drive high-speed centrifugal compressors without any gearbox. This is known as direct drive. Turbines are also variable speed drivers that use governors to keep their speed constant and control the amount of steam or gas that's supplied to the turbine during operation. Turbine speed is measured by a control mechanism that actuates a throttle valve to increase in compressors driven by electric motors. Speed is generally limited to around 3,600 RPM. In these cases, the electric motor may be coupled directly to a low-speed centrifugal compressor. To operate the centrifugal compressor at higher speeds, the motor must be coupled through a speed-increasing gearbox. This is known as a gear drive. The gear drive and coupling configuration is often used in the oil and gas industry. Gearboxes can either be an integral part of compressor construction, or they can be external auxiliary equipment connected between the driver and the compressor. Almost all compressor driver applications use some sort of coupling. Couplings are used to transmit motion between two shafts that are almost but not quite in perfect alignment. They must also be able to withstand changes in compressor load or stoppage of the driver altogether. Now, there are two types of coupling connect the driver to the centrifugal compressor: the gear coupling and the flexible diaphragm coupling. Gear couplings are widely used in high-speed, high-load compressors. They work by allowing their parts to slide or otherwise move relative to one another, with no deliberate bending or flexing. External teeth on the hub of the coupling are free to rock back and forth or move axially within the internal teeth of the sleeve. Small couplings are sometimes grease-packed. Large, high-speed couplings use circulated lube oil. The flexible diaphragm coupling is commonly used with turbine-driven compressors, where distortion due to heat is substantial. The flexible diaphragm coupling transmits power from the driver to the compressor using a solid, rigid hub on each unit. A flexible metal diaphragm is bolted to the outer rim of each hub, and a spacer connects the two diaphragms. All misalignment is handled by the elastic flexing of these thin web diaphragms, and there is no rubbing movement of any parts of the coupling, and no lubrication is required. These couplings can handle fairly large angles of misalignment between shafts. However, this coupling can tolerate only slight changes in back and forth movement of shafts. There are several factors that affect performance of the compressor. For example, varying the speed of the compressor will vary the volume of gas moving through it. Recycling gas back to the suction side will also alter the performance characteristics of the compressor. So in this way, operators can achieve different results for their compressor. To control performance in some compressors, adjustable guide vanes are installed just ahead of the impeller. These guide vanes slightly throttle the suction gas flow and pre-rotate the gas into the impeller eye. These guide vanes can either be adjusted manually or adjusted automatically with a suction pressure controller. One problem in dealing with gas flow through a centrifugal compressor is surging. Surging is a rapid flow of gas back and forth within the compressor. It is an aerodynamic condition caused by a recirculation of the gas starting near the edge of the impeller. This is similar to the effect of swirling airflow on top of an airplane wing that breaks the lift of the wing and causes a stall. With an airplane, this happens when the pilot attempts to gain too much lift at too low a speed. In a centrifugal compressor, this happens when the compressor attempts to raise pressure too quickly at a flow rate that is too slow. At a given RPM, a decrease in flow rate normally will cause an increase in pressure. However, as the flow rate becomes too small, the gas will separate from the vane tip. As a result, that vane passage loses the ability to increase the gas pressure. When that happens, there will be a slight amount of backflow from the diffuser until lift is regained. If the flow through the compressor is decreased even more, a point will be reached where there's a complete recirculation of flow through all vane passages of the impeller. This causes a large amount of backflow and a violent surge can occur. In addition, these large flow reversals can create loud noises, thrust fluctuations, and damaging vibrations in the compressor. While surge is occurring, the gas is recirculated through the compressor and becomes heated by the compression process. As the gas recirculates back to the impeller into lower pressure, it retains that heat. As it is recompressed to its original high pressure, additional heating takes place. If this is allowed to continue unchecked, the gas will become hot enough to cause a bearing or seal failure. A thrust bearing failure can be caused by thrust reversals that occur from the rapid and violent recirculation of the gas. Sometimes these thrust reversals are so violent they can exceed the load capability of the thrust bearing, causing it to fail. This combination of thrust bearing failure and overheating can be catastrophic to the centrifugal compressor. So some kind of protection must be used to prevent this from happening. That's why you'll find most compressors use a surge detection system. The surge detection system senses discharge pressure variations and initiates a compressor shutdown in the event of a potentially serious condition. A surge control system can also be installed that allows discharged gas to be recirculated outside the compressor to the suction side. The objective here is to keep the flow above the surge point. An anti-surge control valve in the recycle line is regulated with a flow controller that senses the rate of the gas flowing into the compressor. If the flow rate is less than the set point, the valve opens and allows enough recycled gas to enter the suction port to keep the compressor flow rate above the surge point. In addition to anti-surge protection systems, other safety devices are commonly installed on centrifugal compressors and their auxiliary systems. Drivers, for example, must have their own protection devices to prevent them from being damaged by overload conditions. Electric motors are protected from overloads and overheating by thermostats and circuit breakers. Turbines are protected from overspeed damage by governors and overspeed trips. In the different types of compressor bearings, temperature sensors are frequently used to monitor startup and operating temperatures. Vibration monitors are placed at strategic points on the compressor to check for any excessive vibration. Some of them are designed to specifically monitor excessive axial or radial movement of the compressor. Vibration monitors are also connected to control systems that will sound alarms and shut down the equipment if necessary to protect the compressors from serious damage. All right. Now in this section, we've looked at the various drivers and the methods of coupling them to the compressor. We've also seen how the flow of gas is controlled to produce the pressure needed for proper processing and handling. And finally, we showed you some of the safety features the compressor and its auxiliary systems use. Well, that wraps up this module on centrifugal compressor principles. By now, you should have a fairly good understanding how centrifugal compressors do the job of compressing gas and how they're configured for use in the oil and gas industry. Take some time and think about everything we've covered. Then answer the questions in your student manual. If you have any questions, play the tape again or ask your instructor. See you next time.